Okay, so our next talk is Tony Jebara, who somehow got cartography in Esquire magazine, among many other accomplishments.
Thanks. Okay, so I'll be giving a slightly different flavor of a talk. It's focused a little bit more on the machine learning side of sparsity, and I'll be talking about how we can incorporate sparsity in some learning problems, and in particular when we have multiple learning tasks. And what I'll do is I'll cover, first of all, this kind of idea of adding constraints in the generative learning paradigm, which is a classical approach in machine learning, and then show how we can make those constraints yield sparsity, and then multitask sparsity, and then talk about some of the solution methods, which basically become sequential quadratic programs. Okay, so the simplest scenario is I give you some data set which contains a bunch of x's and y's. For example, the x's might be x-rays of tumors, and y is a binary label saying, is the tumor benign or is it malignant? And these are coming from some unknown distribution, p, x, comma, y, and your goal is to find a rule that guesses benign or malignant from the x-ray, the x vector, let's say that's the x-ray, and hopefully you get low error when you do this prediction. So generative learning is this Bayesian approach which says, let's try to recover this distribution. And the way you do that is you assume some kind of family of possible models. So a family of relationships between x and y, for example, linear or linear Gaussian. And then you assume some prior of how you're going to pick one of those out of that family. And then you get a posterior distribution, which is p of theta given the data, which says take your prior and multiply it by the likelihoods of all your observations. And that's how you should adjust your view of how the theta was chosen in accordance to the data you've just observed. Now I've got this idea of what the distribution looks like from my set of priors, assuming a family, and then I make a prediction which says, let me vote all the possibilities according to this posterior, and then say, what's the y that gives me the largest value of that vote? And that's the generative approach. Of course, this is suboptimal because you're trying to estimate a distribution over everything. A smarter thing to do is to be a conditional Bayesian. And there you say, I'm just going to consider conditional distributions relating y and x. And I'm not going to care about putting a distribution on x. And you assume a family of those conditional distributions. You also assume a prior. You say, I think, these are going to be generated from some distribution. And when you observe the data, you get a posterior, which is, again, a product of the prior times all these individual likelihoods of all the observations. And then you vote all your conditional distributions using that rule, which says pick the y that gets the highest vote after I integrate over all those models using that posterior distribution. So what's the problem with this framework? It turns out if you make incorrect choices for the model and the prior distribution over the models, you're going to get high test error. And so how do we fix this kind of problem with these classical approaches in Bayesian learning? Well, one idea is to add constraints and say, I want to make sure that while I'm doing this style of learning, estimating these types of distributions, I always get the correct prediction on my training data. So I don't want to make any mistakes on the example tumors you've shown me. I want to make sure that I always guess the correct y after I've followed these rules. And I guessed by a certain amount of margin, so I'm guessing safely. And so let's see what they're doing when they're, let's say, giving these solution distributions, these posteriors. One way to view what's happening is I'm picking the posterior I'm going to use as the distribution that's as close as possible to this product of the priors times all these likelihoods from my t observations. So that's the solution. I'm going to use that in that prediction rule upstairs and plug in the q that minimizes that distance. Well, of course, the best q is simply set q equal to the right-hand side of the KL divergence, bring it as close as possible. So instead of letting the standard Bayesian approach pick the q it wants, which is that q equal to this product, we're going to add some constraints. I'm going to say use the q so that if I actually make predictions with it, I always get the right answer on all the examples. So don't just pick the q that's as close as possible to your prior times likelihoods. Find a q that also, when I use it in that prediction rule at the end, is not going to mess up on any of the examples I've shown it. And so this is just exactly the prediction rule we saw upstairs, but it's a bunch of constraints saying, make sure the true y beats all the incorrect y's by at least a margin of gamma. Okay, so this is a nice problem. The issue with this, and we'd like to solve this, is it's going to cause some non-convexities and so on. So what we're going to do is we're going to change it a little bit and just make these log constraints. And this actually simplifies the problem and turns it into a convex optimization problem in a dual space. And this is known as the maximum entropy discrimination framework. And here I've just added some slack so that you can, with some slack variable, give up on a few examples. Let's say someone mislabeled an X and called it benign when it was really malignant. And so this was proposed in '99 with some collaborators, Tom Yakla and Marina Mela. What's nice about this is it allows some misclassification of the training data, and it also says let's try to come as close as possible to what the Bayesian wants to do, but also make sure that we're getting correct predictions on our training data. And so here's the primal problem upstairs, and it turns out that primal problem is a standard maximum entropy problem, and it can be solved in closed form to yield this dual. Well, there's still the caveat of actually estimating these lambdas. That's a dual optimization problem. But the final answer is this distribution Q, which again looks like a product of all your likelihoods with some prior, but now you take those likelihoods to various powers of lambda. So what the Bayesian was doing was setting all the lambdas to 1. We're going to try to find some other lambdas that are better, and then take the product of all those likelihoods raised to different lambda powers times the prior. And that's going to give us the Q distribution. Because we're doing this all in a dual space, it's actually now an optimization over t scalar parameters, lambda 1 to lambda t, which is the power you want to take the likelihoods to in that product. Okay, so one nice thing about this is it, under some simple assumptions, gives back the support vector machine. And we showed this a while ago. So if you set the model to be a log linear model up there, so something like x times some slope plus b, so you're trying to separate the tumors by a line. And if you set the prior to be a Gaussian prior over the slopes, so I'm going to assume before I see any data that the slopes of the line come from some Gaussian distribution, then the actual optimization problem we get out of the dual is exactly the support vector machine optimization problem. It's the same classification problem and the same prediction. And you can solve this with cubic time with quadratic programming, or with some of these really fast methods like Pegasus, you can get to epsilon very, very quickly. In some situations, you can get sublinear. It depends on the assumptions. Okay, so what we'd like to do is do feature selection and get sparsity out of this. And so in addition to just having a linear model, what you can say is I want to have some binary variables that delete some of my input dimensions. So for every measurement, x, you also have a switch s, which says, can I keep this measurement or do I have to hide it? And so I want to try to censor as many of my measurements as possible while still classifying properly. And so there's a censorship binary variable called s. It's a vector, and it's going to delete certain entries of my measurement. And then I can also make a prior assumption on that binary variable. I can assume it comes from a Bernoulli distribution, which likes to turn off most of the features, and this is going to encourage sparsity. And so now I have this prior. I again apply the exact same framework, and this prior has a parameter rho or alpha, which controls the amount of sparsity I want. And then the dual just becomes this simple expression, which if alpha was equal to 0, which means no sparsity, you get back the quadratic SVM problem. And so now this is in a dual space, doing some kind of sparsification of the signal, while also classifying it as benign or malignant afterwards. And the prediction rule is down below, and it's basically telling you what x's to delete, what dimensions of the x's to delete, which ones to keep, and then you classify afterwards. And so you can examine what type of regularizer you're actually doing implicitly when you're using this Bernoulli switch, which turns off some of these features, combined with a Gaussian prior on the actual slopes. And it turns out, depending on your choice of the alpha or how aggressively you want to throw away features, you're going to blend between an L1 and an L2 norm. And this is, again, figuratively, because you don't quite get the exact L1 norm. There's always going to be a slight smoothness at the origin, which the L1 doesn't have. It gets perfectly sharp. But you can see, in the circles, that's the L1 norm, and in the blue line, that's the L2 norm, and we're going, in the x's is the L2 norm, and as you vary alpha, you're going to go between those two norms. And if you look at a contour plot in 2D, you can see that the dotted line is the L1 norms contour plot, the other dotted line is the L2 norm, and in between is this new suggested norm we're using. And as you modify alpha, you go from the diamond to the circle. Okay, and this is not an exact mathematical, it doesn't coincide exactly with the L1 norm, like I said, but as you plot it, you see it's very, very close. And so once you use this, you end up with, again, a sparse version of the classifier, a sparse version of the SVM, which throws out features while it tries to separate, let's say, tumors and says if they're benign or malignant. Here's an example as we're trying different values of alpha or rho, and the error rate for the SVM is about 92% on this classification problem. As you try different levels of sparsity, you start to ignore parts of the signal that have nothing to do with a labeling problem, and you get much better accuracy. So you can also use this to do kernel selection instead of feature selection. So instead of just removing certain dimensions in your measurements, you could say I'm going to use a variety of, let's say, similarity measurements between my inputs, and I don't know which one is the best one. And so you can pick from many of these different mappings to Hilbert space, which are equivalent to picking a kernel, again by having a feature selection vector S, which says I'm going to use these and not those. And so this, again, with the same type of Bernoulli prior, will remove some kernels and only use others. And so this allows you to have one of these automatic kernel choice SVMs. So if I don't know which kernel to use in SVM, I can use this technique, and with the appropriate choice of the prior, I'll throw out a few of the bad kernels and keep around only a handful of the good kernels. And again, this is all a simple convex optimization problem in the dual over here. Okay, and then one last twist is if you have multiple tasks. So let's say I want to find the best features to use or the best kernels to use, not just to solve a single task, but to solve many tasks. So for example, if a patient walks into a hospital and you want to diagnose them for, if they have cancer or if they have diabetes and if they have some other disease, let's say the flu. You want to minimize the number of tests you want to do on that patient because they're all invasive. You might say, I can do 100 tests, but what's the minimum subset of the tests I can do? Maybe just 5 measurements so that I can predict accurately on the 3 diseases I'm trying to classify if they are present or absent in that patient. And so we can have a version of kernel selection or feature selection where we have multiple tasks. And there you say, I want all the tasks to agree on the same set of features that they're going to use. So I want a sparse set of features, and I want to solve multiple classification problems. And it turns out this can be, again, plugged into the framework. We have extra constraints for all these extra tasks we're solving. You still get the same type of optimization problem. It looks, again, like an SVM when alpha is equal to 0 when you say no sparsity, because if all the tasks are using all the features, they don't need to talk to each other. You can solve a bunch of independent SVMs. But if I say I want sparsity, then all the tasks have to jointly optimize this larger convex problem because they're looking for a single common feature selection. And so I'm not going to talk too much about the details, but the key is as you do this multitask sparsity on, for example, one of these multitask data sets, so Larry has a nice landmine data set where you're classifying many landmines in different ways. Forcing all the different classifiers to agree on what that sparsity pattern should be is going to improve the performance. And what we see is, again, higher area under the curve performance for these 29 different tasks. And so now I'll just talk about what this objective function looks like in the dual. So in the primal, it looked like this blend between L1 and L2. But in the dual, it looks like this. It's a sum of log quadratic function, exponentiated quadratic functions with these constant alphas. And so those alphas are annoying because if they didn't exist, the log and the x would cancel out and we just get a quadratic program. So it turns out this is actually not such a bad optimization problem. Even though it's not a quadratic problem, what we can do is we can replace these log alpha plus exponentiated quadratic terms. Each one of those can be replaced with a lower bound, which is a quadratic lower bound. And so here's a bound we've written up, and it's basically just a quadratic in the variables of interest that applies to this negative logarithm of alpha plus an exponentiated quadratic. And so if you replace all those log terms with lower bounds that are quadratic, you then end up with a quadratic program, and then we know how to solve that. And this is a variational bound, so then you can iterate this whole bounding process and then find a better bound, solve the QP again, find a better bound, solve the QP again. And this is the basic recipe. And we find the bound in step 3, and then we solve the SVM problem. Since it's now just a quadratic program, we've replaced all these non-quadratic terms with quadratic lower bounds. There are very fast solvers to solve those SVM problems. We get a lambda or a solution in the dual, we find a better bound, and we keep moving in this kind of variational optimization. And so this is a very simple algorithm to code up. You basically reuse the code out there for step 4, and you just replace all these terms with bounds. And what's interesting is you don't have to iterate this process too much. So you don't have to keep doing sequential quadratic programming for a billion iterations. We have a guarantee that it will get to within epsilon of the optimal solution within this number of iterations, which doesn't depend on the size of the problem or the number of tasks or how much data you give it. It only depends on how much sparsity you want. So it's going to have a constant factor increase on the work of an SVM. And so here's a proof of that convergence. It's because the optimization problem we have, that log alpha plus exponentiated quadratic, that's in the blue line. It can be lower bounded with a red quadratic, and it can be upper bounded with a black quadratic. So you have a quadratic sandwich on this objective function you're trying to maximize. Since you have a quadratic sandwich like this, you can guarantee that sequential quadratic programming is going to finish pretty quickly. Okay, another thing what you can do with this framework is estimate the structure of graphical models. And so the goal is I have, let's say, 25 binary variables I'm observing. I observe a few samples of these 25, there's a vector of 25 binary variables. Which graphical model did this data come from? So this is the graphical model structure estimation problem. So out of all the possible graphs I can connect these 25 variables with, which one is the graph that's most likely to match the data I've observed, if I'm observing some binary samples. So this is basically the structure estimation problem for an Ising model. An Ising model is a distribution which has the following, so it's a distribution over, let's say, binary vectors, and has the following form. There's a linear term in the binary variable, and then there's these pairwise quadratic terms between pairs of x's. And the parameters of the distribution are a symmetric matrix, which is binary with 0 on the diagonal, which tells you what the undirected graph is that underlies this model. Okay, so that's an adjacency matrix. And then there's theta, which is a scalar matrix, which tells you the relationships between the variables. So not just establishes what the dependencies are, but says how are they related, let's say, linearly. And then there's another singleton vector, eta. And somebody samples some x's from this distribution. I don't know eta, I don't know theta, and I don't know s. But what I'd like to get is recover an estimate of s, the actual adjacency matrix, and say this is the shape of the graph structure that generated this data. And so that's the goal. You're given some IID samples, x1 to xt, which are d-dimensional binary vectors, and I want to recover the structure of that Ising model. Turns out there's a very nice approach to doing this by Martin Wainwright and Pradeep Ravikumar and John Lafferty, and then there's been a lot of other work as well. But this is one method we'll be focusing on. And the idea is you can recover a good estimate of S that's got a lot of very nice theoretical properties and asymptotic consistency and so on by solving D little regression problems. The sparse regression problems with L1 sparsity, you basically penalize the L1 norm of vectors, theta, that relate each individual binary variable to all the others. So I'm trying to predict each variable from variable 1 to variable d using all the others. And I learn a sparse regression that goes from everyone else to variable 1, then everyone else to variable 2, and I learn d separate sparse regressions. Those are these theta vectors. And then I have to then combine all these separate regressions into an actual estimate of the graph structure. And so there are two possible ways, two possible rules. I can say if m used n and had a non-zero value on its relationship with n, and so n was useful to predict the value of m, and m was useful to predict the value of n, so the and rule, so there's some non-zero slope on the theta to go from m to n and the theta to go from n to m, then I'm going to say there's an edge between nodes m and n. That's the and rule. You can also use the or rule, which says if either variable needed the other in its regression, then I'm going to draw an edge in that graphical model. And so both of these will yield some really nice asymptotics. But what we thought we could add to this was forcing the logistic regressions to agree on the symmetry a priori within the optimization instead of doing it as a post-processing step like this. And so you can say, I want to force the symmetry of the anding and oring. I want to bake that into the optimization. I want to find a bunch of sparse regressions from all these variables to each other, but I want them to all be consistent in who uses whom. So I don't have to follow up with an and an or rule. So of course this is going to tie together all the different regression problems. They're not going to be solved d times independently because they all have to agree. And so here's the predictive distribution. Again, it's simply saying every single x is going to get a certain vector of slopes for the mth task, and there's a pattern S which is binary, which tells you which features can be used for the mth task. So can I use, let's say, the third dimension to predict the second dimension? That's the S variable. So it's the same setup as we've had before, but now what we can do is throw in a slightly different Bernoulli prior on S, which says, I want a Bernoulli prior, make S sparse, but also I want the Bernoulli prior to force S to be symmetric. Okay, so we can have that baked in. And then also use the usual Gaussian prior on theta. So the same type of thing, but we're now forcing symmetry on S. And it turns out in the MED framework, in the dual, we get back a convex optimization. So we don't have to solve these separate, let's say, logistic regressions or L1 sparse regressions. We can solve one big convex program which forces all these sparse regressions to agree on the sparsity pattern. And we don't have to use an anding and an oring at the end. And again, because of this form, this looks just like what we had before. It can be solved with that simple quadratic bound and sequential quadratic programming, and you'll finish pretty quickly. And so if you compare this on synthetic data, where you actually sampled binary vectors from several Ising models, you see that the MED technique, depending on the alpha parameter, will perform better than the L1 with anding and oring. Of course, this is just one early experiment. We still have to do a lot more, but there is some value in forcing the sparsity pattern to be symmetric up front versus symmetrizing after the separate optimization problems. And what's nice is this really pops out very easily with this framework. We've also added other types of constraints. I just wanted to put a quick plug for them, called relative margin constraints. So just like we said, try to come as close as possible to the Bayesian solution, but make sure you guess correctly and the correct answer beats all the other incorrect answers. We can also add these other really strange constraints which say, but make sure that the correct answer doesn't beat the incorrect ones by too much. It's a little bit of a strange concept. You want the correct answer to beat every incorrect one, but not to completely overwhelm all the incorrect ones. So this is this kind of other side constraint. And it turns out this can be added very easily to all the optimization problems we've talked about. And what this does is it changes the decision boundary that you end up solving in a funny way, and I just wanted to throw this out there. We have some theory to show why this is helpful, but if I give you some tumors, and I label the benign ones as circles and the malignant ones as triangles, and I solve the SVM, that red line is the best solution. It's the solution that separates the good tumors from the bad tumors with as thick a line as possible. That's what the support vector machine recovers. If you add these constraints we just talked about, you're going to solve for this green line. And the reason why is because if you look at the actual projections on the red lines of the data, so on the left picture, if you look at the projections on the bottom, you're seeing that many of these, let's say, malignant tumors are getting mapped to values of +1, +1.3, +2.4, and so on. And the benign tumors are getting mapped to -1, -1.3, -1.8. So there's some spread on the tumors and the actual classification output. That spread is what we're trying to control. And in the green projections, which is the solution we're proposing, you're saying as much as possible make all the positive examples map to +1 and all the negative examples map to -1, and don't allow any spread like this. And it turns out there's some nice kind of simple concentration guarantees you can make to show that it's less likely to have an error if you're using the green solution than the red solution. So you can add these extra constraints, just double the number of constraints in your classification problem, not just say classify correctly, but also don't try to have these very large positives and very large negatives. So constrain that. And it turns out this also has another really good, healthy improvement over the SVM. And so we call this the relative margin approach. And all these data sets, it seems to be doing consistently better than the support vector machine because of again, tilting the boundary so that you don't ever have anything that's being predicted as much more than +1 or much less than -1. And we've also extended this in structure prediction settings, but I'll skip this slide in the interest of time. So just to summarize, what we've done was taken the generative learning paradigm, which tries to estimate distributions from data, and said let's add some task-relevant margin constraints so we don't make mistakes on the training data. And this is called maximum entropy discrimination. It leads to very nice convex optimization problems in the dual, and we can quickly add sparsity, multitask sparsity to feature selection, kernel selection, and graphical model sparsity. And it looks like a blend between L1 and L2 norms when you look at the actual primal version of it. And again, a nice solver is the sequential quadratic program because we already have all these very fast QPs for these types of problems. We can just iterate them and guarantee in a constant number of iterations we'll finish. So I'll stop there. Thank you. So yeah, that's definitely true. We are ending up with more vectors that are being used in the solution because it's not just the ones that are near the boundary, but ones that are actually far away from the boundary that are helping shape things. Because you don't want to ever predict too large or too small a value. So these really far away samples are also helping adjust the boundary. So definitely we're seeing less, let's say, more examples staying in the actual predictor than the SVM, but we're getting better accuracy. So it could be because of that reason. The analysis we have is because of some other Rademacher bounds, but this might be another intuition that would also yield a similar kind of theory or generalization guarantee. Yeah?
Could you say a few more words to motivate the intuition for the relative margin constraints? I mean, are you affecting the capacity of your classifier?
So you can view it as in some situations, as it's related to some VC analysis. You can do a VC analysis on that. We weren't able to scale that up. It turns out the Rademacher analysis is much more flexible. But one of the really kind of simple intuitions is, and I didn't have a chance to really talk about this, is it's affine invariant. So if I take the data and I apply an affine transformation, and that's what we're showing here, the SVM really starts to change its solution. And whereas the relative margin machine doesn't. In this situation, it's going to stay exactly the same and produce the exact same performance. And I have some animations that show how you can do all sorts of funny affine transformations in your data and really drive down the performance of the SVM, whereas the relative margin technique stays stable. Yeah.
L1 SVM where you get feature selection as well as discrimination. I wondered if mathematically there is any relationship between that and injecting Bernoulli prior on a binary vector. Is there a mathematical relationship?
So very good question. They're not mathematically equivalent. We have a slightly different, like I said, optimization problem. But the goals and kind of the intuitions are similar. So we're trying to do what the L1 SVM is doing, but there's still some L2 regularization built into this method.
Is there a limit on how big of quadratic programming you can do?
So what we're doing is we're deferring to the best quadratic programming solvers, because all we're doing is iterating them and using the bounds. And so some of these solvers are able to handle data sets where, as long as all you care about is generalization error, you can get sublinear, let's say, slowdown. And the Pegasus paper is a good example of that, where you can prove that even if the data set's getting bigger, actually sometimes you need less data to achieve, not less data, less time to achieve lower error, less optimization time, when you talk about generalization error, of course. So yeah, some of these techniques have been applied to millions of examples. And again, this is other people's work. Pegasus is one of the best techniques out there.